How do you determine the speed of light? There have been many experiments throughout the years to try to determine the speed of light, but there's one that really stands out, and that's the one done by Michelson, and that's what I've got diagrammed here. I want to make sure we're clear on why it's difficult to measure the speed of light. It's because it's so fast. So normally we'd say, okay, if I want to determine the speed of light, that's just going to be the distance over the elapsed time. But the problem is it's so fast that you just take some distance, like 1 meter, which is easy to measure. But your delta t is so small, you need an extremely precise clock for that. And that's what makes it difficult to measure. So Michelson came up with this ingenious way to get around that. And as I said, this is his basic setup. He had a light source, and he was shining it on a mirror, like so. And this is a 3-sided mirror. So he shines it on, it reflects off the mirror, comes down to this other mirror, bounces off that, back to our original mirror, but the other side, and then to the observer or the detector. And so if everything's lined perfectly, okay, great, the observer sees it, but actually you can't, as I've stated right now, you can't measure anything, you can't measure the speed of light. What Michelson did to make this really ingenious and to make it work is he rotated the mirror. If the mirror is rotating, most of the time it will be out of alignment. That is, the light will come in and this mirror won't be at the correct angle. And so, yeah, it'll bounce off the mirror, but it won't go straight here to this point on the stationary mirror. It'll go somewhere over here or somewhere over here, but it won't go to where it needs to go, which is right here on this stationary mirror. But at that moment, when the rotating mirror is in just the right spot, yes, the light will bounce right off and go to the stationary mirror. And that's going to happen sometimes because the light source is always on. So it comes down, strikes here, now it comes back. Now, it will not always hit the mirror at the right time. Or better yet, I should say, the mirror will not always be aligned properly. Because depending on how fast the mirror is spinning, if it's just spinning a little bit, then it will have moved from the moment that the light first struck on this side. So when the light struck over here, then it bounced here, and then it comes back, this mirror will have shifted some. And if it shifts just a little, it doesn't have to shift much, then this light will not go to the detector. It'll bounce off this way. Or if it's oriented a different way, it'll go this way. So only at certain speeds, only when the mirror has rotated, say, this much, to where it's rotated that much, will the observer see light. So you have to have just the right rotation rate in order for the detector to see anything. Okay, so what is that rotation rate? Well, first off, let's start with how to calculate rotation. That's omega equals delta theta over delta t. These are actually the two equations that we need, these two here. And this here, so we're going to use this formula. C is d over delta t. So this distance here, we'll call that capital D. And that means that the light has to go there and back. Now, yes, the light also has to do this little bit and this little bit. But if you set it up properly, these are negligible distances, especially compared to this. And so this becomes, 2d over delta t. And I'm going to go ahead and solve this for delta t. So delta t is going to equal 2d over c. And then I'm going to solve this one here as well. This is going to become delta t equals delta theta over omega. Now the key here is delta theta. Now, as I mentioned a moment ago, this has to rotate just the right amount. It can't rotate, any random amount. It has to rotate a specific amount. And what I did before when it rotated is I moved each side over one slot. So there are 3 slots, 1, 2, 3, that each side can be in for the correct orientation. And so I moved it so this side just moved over to this side. So when it was oriented properly, the light actually bounces off of the same part of the mirror twice. So, for example, let me do that again. There we go, rotating that much. Of course, the mirror doesn't change size like mine is, but limits of technology. So in that case, the mirror has rotated 1/3. But I could have the mirror spin faster. And if I have it spin fast enough, then it'll rotate 1/2. It'll rotate 2/3. Or, because there's a third slot, I could have it spin even faster. 1, 2, 3. So, and I can continue this. We could do 4/3, 5/3. Essentially, what's going on is the bottom number is just the number of sides, or you might think of the number of slots for the mirrors to be in. Okay, but the number of sides, in this case I have 3, and the top is essentially how many slots the mirrors have moved in between the light striking the mirror, here, and then coming back. It's how many slots has it rotated through. So if I write that as a general formula, then I'm going to write delta theta as, I'm going to use in for the number of slots it's rotated through, and in sides, over in sides. So now I can set, since both of these equal delta t, this expression and this expression, I can set them equal to each other. And so I have 2d over c equal to in. I'm going to put that in sides in the denominator now. Like that. And of course, at this point, I can solve for whatever I want to. The things that you would usually solve for would be omega or c if you're trying to determine the speed of light. If I was solving for c, then it becomes 2d omega in sides over n equals c. When Michelson did this experiment, his d was very large. It was approximately 35.4 kilometers. He had his mirrors really far apart. As I recall, he had them on 2 mountaintops. And instead of using a 3-sided mirror, he used an 8-sided mirror. He used a 10-sided mirror. He used he used 8, a 12, and a 16. Excuse me. He used an 8, a 12, and a 16 sided mirror. He used 3 different ones. And he did these experiments, I think the first time he did them was between 1878 and 1883. And then he improved it and came back in 1922, from 1922 to 1926, and did it again. I mean, he did these experiments a lot, and he got very precise values. Not quite the same values that we now take to be for the speed of light, but still the most precise at the time. It was a big step forward in determining the speed of light. And so that's what's going on here. It's a pretty straightforward experiment. You've got a rotating mirror, which has some number of sides. In this case, mine has 3. Again, Michelson used 8, 12, and 16. You've got a stationary mirror. There's some distance between them, and the bigger the distance in general, the better, as long as you can accurately measure it. You've got to be able to accurately measure the rotation rate, but it's pretty ingenious and allows you to accurately determine what the speed of light is.